Hi everyone, a warm welcome to the fourth part of residue integration. Residue integration is based on residue theorem. Residue theorem. If fz is analytic in a simple closed curve C except at a finite number of singularities, say z1, z2, etc. zn, then integral over C fz dz equal to 2 pi I into r1 plus r2 plus etc. plus rn, where ri is the residue of f at zi. In this video, I am going to evaluate a few complex integrals by using residue theorem. We have to evaluate integral over C tan z dz, where C is mod z equal to 1. For evaluating this, first you have to find its singularities. See, you can find its singularities by considering tan z as sin z by cos z. And singularities of tan z are given by cos z equal to 0. See, cos z is 0 for z equal to pi by 2 plus or minus pi by 2 plus or minus 3 pi by 2 plus or minus 5 pi by 2 etc. That is, z values are minus pi by 2 plus pi by 2 minus 3 pi by 2 3 pi by 2 etc. So you have to remember sin z is 0 for z equal to 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. You know sin z is 0 for z equal to n pi. So z equal to 0 minus pi plus pi minus 2 pi plus 2 pi. For these values sin z is 0. And also you keep in your mind cos z is 0 for z equal to these values. See, these are the singularities of tan z. Let f is z equal to tan z. So singularities of f are minus pi by 2 plus pi by 2 minus 3 pi by 2 etc. See, among these singularities you identify which are within C. Our C is the unit circle. Clearly, see, pi is 3.14. So pi by 2 is 3.14 by 2, which is greater than 1. Similarly, minus pi by 2. So clearly, no singularity within C. All the singularities of f are outside of C. That is, no singularity of f within C. So by Cauchy's theorem, you can say integral over C f z dz is 0. So the value of the given integral is integral over C tan z dz equal to 0. Next, we have to evaluate integral over C tan z dz, where C is mod z equal to pi. See, in the previous question, C is mod z equal to 1. Here, mod z is pi. So you take f z as tan z. So this is sin z by cos z. And singularities of f are cos z equal to 0, which implies z equal to minus pi by 2 plus pi by 2 3 pi by 2 minus 3 pi by 2 etc. Next, you check which singularities are within C. Our C is mod z equal to pi. Clearly, minus half and plus half are inside of C. So we can apply residue theorem, and residue theorem states integral over C f z dz is 2 pi I into r1 plus r2. Let R1 is a residue of f at minus pi by 2. Since minus pi by 2 is a simple pole, its residue is limit z tends to minus pi by 2. Z plus pi by 2 into f z. F z is tan z, that is sin z by cos z. Here, there is no cancellation for z plus pi by 2. In many of the previous questions, there is a cancellation here, but there is no cancellation. So in such questions, you can find its limit by applying Hospital's rule. See, Hospital's rule is, you take the derivative of the numerator and you take the derivative of the denominator. Then you apply the limit. If it is a finite value, you can stop the procedure. If it is not finite, you again apply this rule. You take the derivative of the numerator and take the derivative of the denominator. And again apply the limit. Then the first finite number is the value of the given limit. See, in Hospital's rule, you have to remember that you don't apply quotient rule here. Even though this is a quotient, but in Hospital's rule, we have to take the derivative of the numerator and denominator separately. Let me illustrate it. Here, limit is the tends to minus pi by 2. You take the derivative of the numerator. See, it's a product. So, in the numerator, you apply product rule. So, product rule is first function into derivative of second, that is cos z, plus second function into derivative of the numerator, that is 1. Next, the derivative of the denominator is minus sin z. You put z equal to minus pi by 2 here. So, it is, see, when z equal to minus pi by 2, this term will be 0. And it is sin minus pi by 2. Minus sin minus pi by 2. This will cancel, so it is minus 1. So, the residue R1 is minus 1. Next, R2 is residue of f at pi by 2. And it is limit z tends to pi by 2. Z minus pi by 2 to f z. F z is sin z by cos z. Here also you have to apply the quotient rule since there is no cancellation of z minus pi by 2. So, for applying Hospital's rule, you have to take the derivative of the numerator and denominator separately. So, derivative of the numerator is, since it's a product, so you have to apply product rule. So, z minus pi by 2 into cos z plus sin z into 1 by derivative of cos z is minus sin z. Next, you put z equal to pi by 2. When z is pi by 2, first term is 0 plus sin pi by 2 by minus sin pi by 2. This will cancel and you can see it is minus 1. So, we have R2 is minus 1. So, we have both R1 and R2 are minus 1. So, you put in equation number 1, see it is 2 pi I into minus 2. So, minus 4 pi I. That is integral over C, or if it is tan z. So, integral over C, tan z dx is minus 4 pi I along the circle mod z equal to pi. Next, we have to evaluate another similar integral, which is integral over C tan pi z dz, where C is mod z equal to 1. Here the function is tan pi z, that is sin pi z by cos pi z. Its singularities are given by cos pi z equal to 0, which implies pi z is equal to minus pi by 2 plus pi by 2, 3 pi by 2, minus 3 pi by 2, etc. So, what is Z? Z is minus half plus half, 3 by 2, minus 3 by 2, etc. So, the singularities of the given Fz is minus half, half, 3 by 2, minus 3 by 2, 5 by 2, minus 5 by 2, etc. Among these singularities, it's very clear that these two singularities are within our C. So, by residue theorem, we can say integral over C Fz dz is 2 pi I into R1 plus R2. That is equation number 1. Next, we have to find R1 and R2. Let R1 be residue of f at minus half. It is limit z tends to minus half, z plus half into Fz. Fz is sin pi z by cos pi z. Since there is no cancellation for z plus half, you have to apply L'Hospital's rule. And L'Hospital's rule is limit z tends to minus half. Derivative of the numerator, see it's a product, so you apply product rule. So z plus half into cos pi z into pi plus sin pi z into 1 by derivative of the denominator, it is minus pi sin pi z. You put z equal to minus half. This term is 0. Then next term is sin minus pi by 2 by minus pi into sin minus pi by 2. So, this will cancel and the residue is minus 1 by pi. So, we have R1 equal to R1 equal to minus 1 by 5. R2 is a residue of f at half. And this limit z tends to half is at minus half into f z. It is sin pi z by cos pi z. And its limit z tends to half. The derivative of the numerator, that is here we have to apply the Hospital's rule. So limit z tends to half is at minus half into pi cos pi z plus sin pi z by minus pi sin pi z. You put z equal to half. See, this term will be 0. So sin pi by 2 by minus pi into sin pi by 2. So this will cancel. The answer is minus 1 by 5. You substitute R1 R2 in equation number 1. So it is 2 pi I. R1 is minus 1 by pi. R2 is minus 1 by pi. So it is 2 pi I into minus 2 by pi, that is minus 4i. Next we have to evaluate integral over c. Z by sin z dz, where c is mod z equal to 1. Let f z equal to z by sin z. Its singularities are given by sin z equal to 0. Implies z equal to 0 plus pi minus pi 2 pi minus 2 pi etc. See, among these singularities, 0 is the only singularity of f which lies within C. So by residue theorem we can write integral over C f z dz is 2 pi I into R1, where R1 is the residue of f at 0 and it is limit z tends to 0, z into f z. What is f z? It is z by sin z. Here also there is no cancellation for z, so you have to apply the Hospital's rule, and it is limit z tends to 0. You have to write the derivative of the numerator. Numerator is z square, its derivative is 2z. Derivative of the denominator is cos z. You put z equal to 0. When z is 0, it is 0. So R1 is 0. You put in this equation, you can see integral over c f z dz equal to 0. That is integral over c z by sin z dz is 0 along the curve c mod. Next evaluate integral over c z by cos z dz, where c is mod z equal to 1. You consider the function f z as z by cos z. Its singularities are given by cos z equal to 0, which implies z equal to pi by 2, minus pi by 2, 3 pi by 2, minus 3 pi by 2, etc. See, our circle is mod z equal to 1, its radius is 1. So clearly all the singularities are outside of C. So you can apply Cauchy's theorem. And by Cauchy's theorem, integral over C f z dz is 0. That is integral over C z by cos z dz is 0. Next we have to evaluate the integral. Integral over C e raised to z by cos pi z, where C is mod z equal to 1. You consider f z as e raised to z by cos pi z. Its singularities are given by cos pi z equal to 0, which implies pi z is pi by 2, minus pi by 2, 3 pi by 2, minus 3 pi by 2, etc. So what is z? Z is half minus half, 3 by 2, minus 3 by 2, etc. See, clearly among these singularities, these two singularities are within our C. Since two singularities are within C, by residue theorem, integral over C f z dz is 2 pi I into R1 plus R2. That is equation number 1. Next we have to find R1 and R2. You take R1 as residue of f at half, and it is this limit is that tends to half is that minus half into, that is f z e raised to z by cos pi z. Here also now cancellation for z minus half. So we have to apply L'Hospital's rule. So limit z tends to half. You write the derivative of the numerator. See, it's a product. So there you apply product rule. So first function into derivative of second plus second into derivative of first divided by minus pi sin pi z. Next you put z equal to half. When z is half, this term will be 0. So e raised to half by minus pi into sin pi by 2. Sin pi by 2 is 1. So the answer is root e by minus pi. So we have R1 is minus root e by pi. Next we have to evaluate R2. What is R2? R2 can be taken as a residue of f factor minus half. That is, limit z tends to minus half. Z plus half into fz. That is e raised to z by cos pi z. That is, limit z tends to minus half. Z plus half into e raised to z plus e raised to z by minus pi sin pi z. You put z equal to minus half. See, this term will be 0. So e raised to minus half divided by minus pi sin pi by 2. Sin minus pi by 2. That is e raised to minus half by plus pi. So R2 is 1 by, so you can write it as 1 by root e into pi. So 1 by pi root e. So this is our R2. You put this in equation number 1. You can see it is 2 pi I into minus root e by pi plus 1 by pi into root e. Pi will cancel each other. You can see it is 2i into 1 by root e minus root e. See, this is the value of the given integral around the unit circle. Next, we have to answer another interesting question which is entirely different from all the previous questions which we have answered. So consider the integral. Integral over c log z dz, where c is mod z equal to 1. See, here we have to integrate log z along the unit circle. On the unit circle, z is really e raised to I theta for 0 less than equal to theta less than or equal to 2 pi. We have to integrate log z along the circle. On the circle, z is e raised to I theta. So log of e raised to I theta into dz. What is dz? I e raised to I theta. So I into e raised to I theta d theta. dz is I e raised to I theta d theta. Here we have to put the variation for theta. Theta varies from 0 to 2 pi. So for evaluating this integral, you have to evaluate this integral. That is, integral 0 to 2 pi log e raised to I theta is I theta into I into e raised to I theta d theta. That is, I into I is minus 1 minus integral 0 to 2 pi theta e raised to I theta d theta. You can evaluate this product by integration by parts. You do it in your own way. Here I am doing in a shortcut method, and the shortcut method is you start with theta, then assign alternative sign starting with the plus sign. You write its derivative here. Next you consider the second term. You write its integral here. It is e raised to I theta by I. Here you write its integral, that is e raised to I theta by I square. Now integration is over. Before applying the limits, you have to simplify the signs. That is minus of theta e raised to I theta by I square is minus plus e raised to I theta from 0 to 2 pi. You put theta equal to 2 pi. So 2 pi e raised to I 2 pi by I plus e raised to I 2 pi minus, when theta is 0, this term is 0, when theta is 0, e raised to 0, it is 1. That is minus 2 pi by I plus 1 into, see from first two terms you can take a common factor e raised to I 2 pi minus 1. What is e raised to I 2 pi? E raised to I 2 pi is, e raised to I 2 pi is, e raised to I, theta is cos theta plus I sin theta. So e raised to I 2 pi is cos 2 pi plus I sin 2 pi. Cos 2 pi is 1, sin 2 pi is 0, so its value is 1. So it is minus 2 pi by I plus 1 into 1 minus 1. So it is minus 2 pi by I. Again 1 by I is minus I, so it is 2 pi I. So the value of the given integral is 2 pi I.